Hello everyone, we are finishing the topic of operational amplifiers by looking at three other functional circuits using op-amps that are active filters, integrators, and differentiators. So let's get started. First, let's take a look at how we can use op-amps as active filters. This circuit configuration is similar to the inverting amplifier configuration that we've seen before, with the difference that previously we only used resistors in the amplifier circuit, but now we would like to see what other functional circuits we can build if we change the resistors to impedances or the frequency dependent components. So we're going to have Z1 in the feed in path, so Z1 connects Vi to the inverting terminal, and Z2 in the negative feedback or feedback path that connects V out to the inverting terminal of op-amp. So V out over Vi, just like as we saw before, equals to negative Z2 over Z1, and now both Z1 and Z2 are frequency dependent components, meaning that both their magnitude and phase changes with frequency value of the input signal. So the gain is frequency dependent. This time we're going to show the gain with H of S or H of J omega when we do the frequency, when we want to find the frequency response of this circuit. So H of J omega is equal to the Z2 over Z1. I'm going to represent H of J omega in the polar format. So H of J omega is going to be magnitude of H of J omega multiplied by e to the j phase of H of J omega. If you have a complex number z equals to a plus j times b in Cartesian coordinate system, so if you want to write it in polar format, you can write z equals to magnitude of z times e to the j theta or angle of z. So this is a similar situation. The only difference is that H of J omega, both magnitude of it and phase of it are dependent on the frequency value or omega value. So the first active filter that is implemented with op-amps that we're going to see today is a low-pass filter using op-amp. So I'm going to write H of J omega as V out over V in. That is going to be equal to negative Z2 over Z1. Now Z2 is R2 in parallel with the impedance of the capacitor, and that's going to be equal to R2 in parallel with 1 over J omega times C2. This is the impedance of a capacitor. So Z2 is going to be equal to R2 divided by 1 plus J omega C2 times R2. From there, and Z1 is equal to R1. From there, a H of J omega, or the gain, frequency dependent gain, is equal to negative R2 over R1 divided by 1 plus J omega R2 C2. If we draw the magnitude of H of J omega as a function of omega, you're going to see that this circuit operates as a low-pass filter, functions as a low-pass filter. So if I draw magnitude of H of J omega as a function of omega, for omega equal to 0, the gain or the magnitude of the H of J omega is going to be equal to negative R2 over R1. This is going to be a positive value because I'm drawing the magnitude of H of J omega. And as omega goes to infinity, the magnitude of H of J omega is going to go to 0. So it's going to operate like this. This is the magnitude plot of a low-pass filter. This filter is going to pass the input signals with low frequencies, and it's going to attenuate the signals with high frequencies. The other active filter circuit using op-amp is a high-pass filter. You can do that. You can implement it by placing a capacitor in series with R1 in the feed-in path that feeds Vi to the input of the operational amplifier. So again, H of J omega equals to negative equals to V out. H of J omega equals to V out over Vi. That's equal to negative Z2 over Z1. This is my Z2, and this here I have Z1. Z1 equals to R1 plus ZC, which is R1 plus 1 over J omega times C1. Now H of J omega is going to be equal to negative R2 over R1 divided by 1 minus J multiplied by 1 omega times R1 C1. This circuit is going to operate as a high-pass filter for omega equal to 0. The magnitude of H of J omega goes to 0, and for when omega goes to infinity, the magnitude of H of J omega is going to get close to R2 over R1. So if I plot a magnitude of H of J omega as a function of omega, it's going to look like something like this, and it's going to reach the value of R2 over R1 for large frequency values. The next functional circuit that we're going to see today is an integrator that's built using op-amp. In this circuit, a capacitor connects Vout to the inverting terminal of the op-amp. Let's start solving this circuit, and by that I mean finding a relationship between Vout and Vi. I can write the current I that as labeled in here. This is the current that flows through the capacitor, so I know that I equals to C dVc over dt, which is voltage across the capacitor equals to Vout minus Vn divided by dt. And I'm going to assume an ideal op-amp, so because of the presence of the negative feedback, Vn is almost equal to Vp. Vp in here is equal to 0 because positive terminal is connected to the ground. From there I can write I equals to C dV out divided by dt, and this is C2, and this is also C2. This is my Vn. I also know that I is equal to, in this path, this is the same current because no current goes into the op-amp, so the same current flows through R1. From there I know that I equals to Vn minus Vi divided by R1. Again, Vn is equal to 0, so I equals to negative Vi divided by R1. From there I can equate these two equations, this one and the top one, and if you do that, negative Vi over R1 is going to be equal to C2 dV out over dt. And from here, dV out over dt is going to be equal to negative 1 over R1 C2 times Vi. And if I solve this differential equation, V out of t is going to be equal to V out of, at time t equal to 0, the initial value of the voltage across the capacitor, minus 1 over R1 C2 integral of Vi of tau d tau starting from 0 to t second. So this is the equation that relates V out to Vi in time domain, and as you can see, this is an equation of an integrator. So this circuit integrates the input signals until time t and scales it with a coefficient of 1 over R1 times C2. Let's look at the second circuit, that is a differentiator circuit, and we would like to find an expression that relates V out to Vi. Again, in here I can write an equation for I, and this is Vn, this is Vp. So I is equal to Vn minus V out divided by R2. Also, the same current flows through the capacitor, so I is going to be equal to C dVi minus Vn over dt, and that is equal to C dVi over dt because Vn equals to Vp, and that's equal to 0. From there I have V out of t equals to negative R2 C1 dVi over dt. So this one differentiates the input signal and then multiplies it by a coefficient that's equal to R2 times C1 and operates as a differentiator circuit. In summary, today we saw 3 different applications of op-amps. One of them was using op-amp as active filters. We looked at 2 different filters, a high-pass filter and a low-pass filter configuration using op-amps. Then we saw application of op-amp as a differentiator and the op-amp circuit that functions as an integrator. Thank you for watching.